Hi, and welcome to this tutorial video of the advanced configuration of AutoGaitA Deep Lab Cut. Please note that there are separate videos for the main configuration and the main workflow, as well as for proper file preparation. However, looking at the advanced configuration, I'd like to start with the customized joints and angles area, where we separated the joints that we analyze into primary and secondary joints. Primary joints are those that are included in all analysis. So for these, you get velocities and accelerations. These are also later translated to the group toolbox, and you're then able to select the, for example, knee acceleration as a feature for your group analysis in its statistical or PCA approaches or tests. Secondary joints are just included in the stick diagram, so in the secondary joint stick diagram. So we create a stick diagram of these joints with respect to the step cycle or behavior of interest of primary joints. So in this very straightforward case that we have right now, primary joint is the hind limb of a mouse, secondary joint is the forelimb of the mouse, and the secondary joint stick diagram is just telling you what was the forelimb doing while the hind limb was performing individual steps. You can use these two buttons here to add joints. You can leave boxes empty if you want. And then moving to the angle configuration, you can again just add angles and leave boxes empty. And tell us here what a given angle name is. So for example, the ankle and how it's computed. What is the lower joint and the upper joint that make up this angle, for example, the ankle. And the ankle is computed between the hind paw, the ankle, and the knee. Or as another example, the knee is computed between the ankle, the knee, and the hip. That's it for the joint configuration. Now for the baseline or beam configuration, if you have a beam that you would like to standardize heights to, we separate it into left and right beam. And here in the first row, you enter what the left beam column and the right beam column is called in your data. And I put the primary and secondary joints in parentheses here, because primary joints, so the joints you put in this column here, are automatically standardized to the left beam, and secondary joints are automatically standardized to the right beam. And the next row is joints or is a section to include joints that are not included in primary and secondary joints, but that you still want to include in your beam standardization. So this is what I call beam subtraction joint. So for example, the tail for us was not included in primary joints, but is still on the left side of mouse bodies. Remember that we are also adjusting x coordinates and simulate that all mice are walking from left to right. Okay, so then because we do this, we know that the tail is always on the left side of the video frame and is then standardized to left beam. And again, similarly for the right beam, the nose and the ear base are not of analysis interest. However, so that we are sure that the Excel files that we generate in the end make sense, we should include these joints in the beam standardization as well, because otherwise the nose and the ear base would have like massively different y coordinates because they were not included in the beam standardization. Again, you can choose these buttons here to add joints. Now let's say we're done with these. We can move to the advanced configuration. The advanced configuration window is separated into analysis and output. For analysis, it starts with the criterion you want to implement for rejecting step cycles. So this is the criteria we use for checking if deep lab cut tracking has failed. And we have two criteria for the X and the Y dimension, so for the horizontal and vertical dimension. And what these do is they just check if from one moment to the other, so from one frame to the other, in a given step cycle, any of the columns of your primary joint, so this is only for primary joints, have changes of this value or larger along X or Y. And if that is the case, we automatically reject the whole step cycle as being broken, because we assume that such a large shift from one frame to the other can only be due to deep lab cuts tracking having failed. So make sure that you have rather large values here, because if deep lab cuts tracking should fail, it's typically accompanied with pretty big changes in these values. So we know, for example, that a mouse would never, by nature, suddenly change any x coordinate from one frame to the other by 200 pixels or more. So if we should observe this, we know that it's a deep lab cut failing for that given frame, and then we throw out the step cycle. For the next two boxes, you can choose to analyze accelerations, and that means that we plot and export accelerations, and this also means that accelerations will be available or not in the group toolbox's feature selection window. You can then choose to standardize your y coordinates separately for all step cycles. So this makes sense if you know that there's some shifts on your floor, or if the floor is uneven, or maybe I don't know, your room is tilted or something. Then you can choose to standardize y coordinates separately for all step cycles, and then we do that. However, note that if you should standardize y coordinates to a beam, this is automatically not done, because then we assume that because it's the same beam that your animals walk on, this is not necessary. Next, you can, if you don't standardize y coordinates to a beam, your y coordinates are standardized to the global minimum by default. And here you can choose to standardize y coordinates to a given joint. So for the hind paw of our mouse data, this doesn't maybe make too much sense. However, consider the case of someone being interested in a human, I don't know, human arm movement, and they would like to standardize to the elbow, because they told subjects to keep the elbow fixed, so they know that the elbow doesn't change in height, and then they just want to look at, I don't know, hand movements or something like that. Then it probably wouldn't make sense to set the y coordinates to the global minimum, because the global minimum would be the foot of people. So this is if people want to use a joint instead. Now we can choose to analyze x-coordinate averages, standardize x-coordinate averages, and also to which joint x-coordinates should be standardized to. In our case of mouse locomotion, analyzing x-coordinate averages means that for the steps that our mice were doing, we not only export or include y coordinates over the average step cycle, but we also export the average x coordinates over the average step cycle. And because our mice were walking from left to right through the video frame, these averages don't make too much sense without standardization. So standardization in this case means that all steps were made at an x-coordinate of 0. So they all started at an x-coordinate of 0. So imagine that a mouse does one step and is then teleported to the beginning of the video frame, and then does the next step, is teleported back, and so on. So this is what happens if you tick this box here, standardized x-coordinates. You can choose which joint we should use for x standardization. Again, for our case, it makes sense to use the hind paw because we are interested in the hind limb. But then again, imagine, I don't know, you have some human subjects and you're interested in some boxing research, and you would like to assess the velocity of the hand. You might want to standardize, or of the velocity of the arm, let's say. You might want to standardize your x coordinates to the shoulder, because maybe people have some stand where the foot are not at equal x coordinates. Maybe one foot is in front of the other, and then it wouldn't make sense to put the foot at 0, but then you would like to have the shoulder at 0, for example. Next, we have the y-axis inversion. So Deep Lab Cut by default starts at the top left corner with sort of counting coordinates or measuring coordinates. So therefore, the more a joint goes to the right, the larger the x coordinate will be, and the more a joint is at the bottom, the larger the y coordinate will be. And what we do is we flip the y-axis so that the more distant a joint is from the bottom, the larger the y coordinate is. So just intuitively, this ensures that the nose, for example, for our mice, has a larger y coordinate than the foot. Just to have things that are higher than other things have larger y coordinates, to have it more intuitive. And this is okay because we have all our y coordinate standardization, right? So whether we standardize to a beam or to the global minimum or to a joint, whether we standardize to a step cycle or not, or separately for step cycles or not, we can invert the y-axis because no analysis of AutoGaitA Deep Lab Cut occurs without some form of y coordinate standardization. Next, we have the output section here, and here you can configure some things for the output we generate. So how many primary joints you want to plot in detail. So since I entered 3, I will get some detailed plots. So with detailed plots, I mean individual step cycle plots. So for example, y coordinates as a function of x coordinates for the first 3 joints here, but not for the iliac crest because that's my 5th joint. Know that if you put 3 here, we will take the first 3 joints of the primary joint column, as I just shown you. Then you can save your sheet files that we generate as XLS files instead of CSV. You can use standard error and standard deviation for your plots. You have a lot of options for the color palette you can use. So these are all the options that C1 provides. Then you can plot legends outside of figures panels, and save the result subfolders that we generate to some specific folder that you like. If you don't enter anything here, we will just create a results folder in your data location and then put all results subfolders in that folder.